So let's now start the last part of the morning session. Now we have a talk by Professor Naresh Dadij. Everybody knows him here, so I think there's no point introducing him. Professor Naresh Dadij will talk about universal features of gravity in higher dimensions.
First of all, it's a great privilege to speak in this meeting dedicated to the memory of Chandra, and I thank the organizers for the invitation. As Sri mentioned yesterday, that in one of his interactions with Chandra, he told him that he could do a accurate verification of Einstein's gravity, and Chandra said, "What's the need? It's such an elegant theory." Now, in a couple of my interactions with Chandra, once he told me that Einstein, after discovered this beautiful theory, the fellow never addressed the relevant issues. And he says that after discovering the theory, what does he get into? He goes on to unifying electromagnetic and gravitation. On the other hand, the relevant question was to formulate the initial value problem for your theory. And that somehow Einstein didn't address till the end, even when Socke-Brouwer at the FEG in 1955 or 54, just before Einstein died, and showed him that she has formulated the initial value problem and it all works. And Socke-Brouwer is on record to say he was not interested. So what? So there could be a situation here that he was so sure that it ought to be true and it could be left for somebody else to do. Whereas for Chandra, this was the most important question he should have addressed to. And but he said, having said this, had it not been for Einstein, we wouldn't have had a general relativity till about 1960s or 1970s. So at some level you should all feel sad that he really stole this kind of an opportunity from the generation of people who started working on this field in 70s or 60s. Okay, now let's come to the cheap stuff. And well, my motivation for doing cheap stuff, I speak on the behalf of the class of people, the community of people who do it. First thing is we are no good for doing anything else. So it's not a question to this thing. And occasionally, cheap stuff also produces something interesting. And so we always keep on hoping for that some occasion to happen. And most often it doesn't, but that's one. Other problem is to pitch a talk in this kind of a mixed audience, which is bipolar. There is no middle layer. It's the one layer of who are adherent of no or the gray hair theorem, and the other part who think that there is nothing better than hair itself. So on my part, since I agree with Sri on one point, that to this gray hair audience there is nothing you can say. because they are never in a mood to listen to. And so I would rather address to the other part of the audience. And secondly, again, I have very simple things to say. No, nothing very complex, only address things at a level of a purely common sense. And occasionally I will throw some catchy words so as to keep my other audience little engaged or little amused. So let's begin with. And the beginning is that one thing which I would like to, I'm quite fascinated by this word, concept of universality or universal, and I'm really going to harp on this and try to see that from a very appealing to this, what is it which we could draw from this? And it turns out that yes, it's a thing which you could obtain quite a lot if you simply look at analyze or probe deep enough the concept of universality. And then I would like to derive the gravitational dynamics from the geometry of space-time. We all know that the Einstein's gravity is described by the space-time curvature, and hence its dynamics, meaning the law of gravity, should follow from the curvature of space-time. It should be a geometric property of the space-time itself without really resorting to any other question. And in the process, we will come across a new constant of space-time, and we will dwell something more about it and try to clear the confusion which many people try to identify this vacuum energy. And I would try to submit that the vacuum energy cannot be incorporated by identifying it with lambda. The next question is about the dimension. Now, when I say gravity is a universal force, by where I would mean is anything universal is there, that means we have no freedom to prescribe anything to it. What we have to do is we simply should really look at the property of this or ask some meaningful physical questions and then simply follow. So similarly, we should also ask the question, does gravity remain confined to a given dimension or does it not? And that's the question you have. So here I would like to build up or rather discuss a couple of arguments and motivations which are purely based on classical theory. Now, higher dimensions is a usual playground for the string theorists. They need no motivation for that. So when I was doing this, I thought the string theorists will be very happy that there is also some classical arguments or motivations being built up. And to my surprise, they were not. It was like as if I was snatching something from them because the higher dimension is their monopoly. And how could there could be a classical arguments for this? Now, if we have a higher dimension, then one should ask the question, what governs its dynamics in higher dimensions? And for that, we will discuss and we would like to see one another piece of universality. We will notice that if I look at the vacuum solution in these higher dimensions of the proper equation, asymptotically they agree with the Einstein solution in higher dimensions. So they have a universal asymptotic limit. And that is again something interesting, or what it means is in some way it is quite expected, because the higher dimensions corrections you look, these are the high energy corrections to gravity, and so whatever you are going to put there, that should be relevant only on the high energy end, but not on the low energy infrared end. And so that's one. Similarly, well, here I was trying to look at some universal features. Is there anything else which could we say? Now again, you have a very simple situation. All of us know about that the gravity inside, the gravitational force inside a uniform density sphere always is proportional to the radius. Now, this is a very simple prototype situation, and so my claim I would like to prove that this should be true for any good theory of gravity. Newtonian theory, it is trivially true, we will see. It should be true for the Einstein theory, which is a nonlinear theory. You have a greater degree of nonlinearity you can introduce by bringing in the higher powers of the curvatures, the Lovelock theory, and it turns out that this remains true in all dimensions. And then we will end up with a discussion. Now, as you know that I'm fairly clumsy in my presentation, so I'm also very clumsy in my the order of the transparencies. So let me start from the very simple, right at the beginning. And all of us understand in the Newtonian mechanics or any mechanics that in the absence of forces, how is the space-time characterized? And the answer to that is that the space is homogeneous and isotropic, and time is homogeneous. So this is a characteristic property of the space-time in absence of all forces, or we can define this as the free space-time. Now, if the space homogeneity allows me that I can interchange x and y, nothing should change. There is also homogeneity in time, and the homogeneity is a general principle. In whatever it is homogeneous about, the same thing should be true. So I should be able to do the same thing of interchange of x and t. Xt, I can convert t into length, and I can have an interchange of x and t. So the point which I would like to say, it is the basic property of homogeneity of space and time demands that there must exist a universally constant velocity. Once I have a universally constant velocity, then space and time are bound together into space-time. And your Einsteinian mechanics called special relativity is born. It doesn't require anything more here, and that's what you have. Then again, I ask the question that I don't take anything for granted, and it will be a question to ask, what should be a geometry of such a space-time? It is space-time which is homogeneous and isotropic and homogeneous in time, what should be its geometry? And that's where our mathematicians tell us that its geometry will be of a constant curvature. It is a space-time which is constantly curved, or that is to say, that is Riemann curvature, covariant derivative is 0. So you have a constant curvature comes in here. So this is the most general geometry of the free space-time which we have. So now this question is, moment you have a constant curvature, what does it mean? The constant curvature gives you the radius of curvature of the space-time. Now, when the radius of curvature is infinite, the space-times become flat. So what we have so far been used to, taking this as a flat space-time of special relativity, what we are meaning is, we are assuming, we are imposing on the general structure that the space-time has infinite radius of curvature. So, on the other hand, the natural question is that the space-time can have a finite curvature. So right here, we come to a very profound statement that whether the space-time is bound with a finite extent, a fixed size, or whether the space-time is infinite. Now, the answer to that, of course, is ultimately it's a gentleman like Sri who has to tell us this, the observation who has to say whether the universe has a finite extent or universe is infinite. Fortunately, that right now it seems to be the observations tell us that what goes by the name of the acceleration of the expansion of the universe seems to say that the universe has a finite extent. And this constant lambda, which we will just introduce, seems to admirably describe the present data, and you need no dark energy. Now this is a very hard statement. Moment you say not dark energy, then you don't have much job to do. All theoreticians always need something to keep on doing. So, but that's the situation. On the other hand, what we need is, let us try to see that we have that this very general property of homogeneity gives us two fundamental constants of space-time. One binds space and time together into space-time, other curves it. And these are the two constants which are now become the part of the space-time structure. No other constant enjoys this degree of fundamentalness. So we ought to take them as seriously. Now let's get back to where I said I should start. Okay, so now let us first ask, you have the Newton's second law. Now, this law is a good law for so long as particle mass is non-zero. Moment I have a particle mass 0, somewhere m0 I have written, then what happens to C? This law is inapplicable to particles with 0 mass. So we don't. But I want to ask, first let us postulate that there is a universal force in which everything which physically exists participates. Irrespective, we don't know what that force could be. So let's postulate there is a universal force. It should also the 0 mass particles should also participate in it, which means this law is no longer valid. So we need a new law. Now, when we are looking for a new law, what we have to take into account to make zero mass particle feel such a force, zero mass particle have one problem, one bad habit, that its velocity cannot be changed. Zero mass particle have that universal constant velocity little c which we wrote, so its velocity cannot change, yet it must feel the universal force. Now, this is a contradiction in the Newtonian framework, because the only way we measure the action of a force on a particle is by simply seeing the change in its motion. And here you say its velocity cannot change, and so what do we do? So we have to do something more imaginative. Could it be that we can curve the space-time, and in which all particles which have to move under universal force follow simply the geometry of such a space-time? Like the straight lines are the free particle motion for the flat space-time, now you have a curved geometry in which whether the particle has zero mass or non-zero mass, but they follow the straight lines of this curved space-time, and they are called the geodesics. And so this is the only way you can make zero mass particle feel the universal force, and all others have to follow. And so, and this all has to be given by the curvature of the space-time, which is described by the Riemann curvature, this RABCD. So this is the question what we have. Two things also we should realize here, that once we have this situation, so we need to now that our usual situation what you have, where when we come to general relativity, we use this so-called principle of equivalence, and where the basis of this, the all particles fall equally fast, and where you did this mi equal to mg, you have a big burden to first explain why the inertial mass should be equal to gravitational mass. Second thing, this anyway does not work for the zero mass particle. So, on the other hand, so here I would say Jonathan Singe has made a very prophetic, very interesting statement, that in his book, The General Theory, that principle of equivalence served a good purpose of a midwifery to general relativity. But now we must realize the absoluteness of the curved space-time, and the midwife could be buried with due honors. So here the question is, once you take the curvature of space-time, then whatever you say the inertial mass, which simply becomes a property of the curved space-time, that at every point on a curved space there exists a tangent plane where you could have your special relativity. Now, so from here, the question I wanted to say is that we should derive the law of gravity purely from the geometric property of the space-time curvature, and the curvature we have is this. It is all should follow from here. Now this satisfies a Bianchi differential identity, which simply say that its Bianchi derivative, which is the antisymmetrized in these three indices, must vanish. Now, just to bring this thing at a more familiar level, this is simply, you know the cousins of this. We all know that the curl of a gradient is 0, your vector calculus. You have a divergence of a curl is 0. So you have this scalar potential to the vector field. Now from this, if you go the next one, then this is what comes about. So this is actually in the same series is the cousin of a divergence of a curl 0. So you have this. Take its trace, it gives rise to a second rank symmetric tensor with a vanishing divergence. So I have this thing. Now from this, it's a simple common knowledge says I can certainly write this equal to something which is a constant relative to this covariant derivative. So the metric is a constant relative to that. And a second rank symmetric tensor asking that its divergence must be 0. So this is, up to this we all come purely from the, driven by the differential geometric property of Riemann curvature. Now, can we make any sense out of it? This equation. What is on the left hand side? I have this thing which is actually a creature of the Riemann curvature. It comes from the contraction of the Riemann. What does the Riemann involve? Riemann involves the second derivative and the square of the first derivative of the metric G. So on the left hand side, you have a second order differential operator, an analog of your good old del square phi of the Newtonian equation. So if this is the second order differential operator, then on the right, if I can identify the source for the force, then this becomes an equation of motion for such a force. Now, the force we started with was a universal force, the force which links to everyone. Right? So its source must also be some parameter which is shared by everything which physically exists. And the only thing which is shared by everything physically exists is energy and momentum. So if you identify with this TAB with the energy momentum distribution, then lo and behold, this is your Einstein's law of gravity. This is the Einstein's equation for gravitation, which has come purely from the Riemann curvature following its differential geometric property. So the universal force which we started with is actually gets identified with the Einsteinian gravity. So Einsteinian gravity is uniquely the universal force. TAB, energy momentum, you would say that it must have satisfy the conservation laws, and this is what is dictated by the equation, that its divergence is 0. Now in this equation, this lambda GAB and the TAB enter in at the same footing. And hence, this lambda should enjoy the same level of importance and significance as the method tensor TAB. So we should not be able to throw it out as we feel like. And why is this point to be emphasized is that the Einstein unfortunately did not follow this route to obtain the equation. He followed the route where first he wrote this GAB equal to TAB without a lambda, and then introduced lambda to get a static solution of the universe. And when the non-static solution came about, then he also or others thought that it's not necessary. And you have the whole controversy came about. Then again, lambda gets resurrected in late 60s when Zeldovich considered the quantum vacuum fluctuations, and whose stress tensor happened to have the same form as this. And so the lambda came up. But then when you compare the lambda with the the Planck length, which was off by 120 orders of magnitude. So again, the lambda went into disrepute, remained again on the people's whims. More clearly, again in 1997, when you observed the accelerating expansion of the universe, it turned out that lambda exactly fits into that data. It doesn't require anything. And remarkably, the value of lambda as determined to have the Einstein static universe is exactly what is consistent with the observation. So that's the situation. Here, what I would like to see is that any equation of motion generally has one free constant, and which you measure by doing an experiment to measure the strength of the force. So here, so that is what is determined by the kappa, gets identified by the Einstein, the Newtonian gravitational constant. Then you might ask, what is this lambda for? Now, let's call back the very first transparency. We said it is the homogeneity of space-time which demanded in a natural fashion that there must exist a constant curvature of space-time. And so this is exactly what is going to be, that if I'm free of all matter, the space-time, this is the equation which has a constant curvature. So the lambda, the size of the space-time, which we say the radius of curvature, is actually now determined by this lambda, which is a maximally symmetric space-time, just to say this. And so question is that this is the most general. So lambda is a true constant of space-time. And more clearly, it is a all matter-free, all gravity-free limit of the space-time. And that's when you, and this, so you would, now, one question would say is, why this additional constant comes about here? The reason for it is that what is new for gravity compared to the rest of the physics, the rest of the physics, you have a fixed background space-time given to you. You don't have that luxury for the gravity. Here, the space-time itself is dynamic, and this is the lambda is actually an indication of that fact. This I have done. So now that a little thing about lambda and vacuum energy and why the two get confused. The reason is that stress tensor for vacuum energy, if you write, it is proportional to the metric. So it has the same form as lambda GAB in the equation, and so that is what. And the vacuum energy also appears in no other way. You have this. But however, we should remember that vacuum energy is created by matter. It does not have its independent existence. So it's not a primary charge of gravity, but it is a charge, it is a secondary effect. Actually, it is at the similar level, at the same level as the gravitational field energy. So how the Newtonian theory, Newtonian gravity is different from Einstein's gravity, because the Einstein's gravity has the gravitational self-interaction, because the gravitational field also has energies. And our general principle is all energies must gravitate, must participate in this. And so now we should ask, how is the contribution of gravitational field energy taken care of in general relativity? And the answer to that is, it is not taken care of by writing a stress tensor, like what we are writing for the vacuum energy people are doing. It is taken care of in a more subtle way, and that is So let's take our canonical picture that we want to consider the field of a mass point, static. So this is a spherically symmetric metric. You write the time component, which could be written as del square A. Here there is a prime over A. I forgot about this. And this is the R1. Now, the null energy condition will tell you, but we want all them to be 0, so I can as well first put R00 equal to R11. And that tells you from this thing, that demands that A dash over A plus B dash over B should be 0, or which demands that AB should be equal to constant, or more clearly, the AB should be equal to 1 if I want space-time to be asymptotically flat. So this gets determined. Now, if this I put it back here, then my R0 naught is simply the del square A, which is the same good old Laplace equation, which should give me solution as 1 over R. So now you might ask the question, where has the self-interaction gone? Or where has the contribution of gravitational field energy gone? Because we all made so much fuss about that I have need to go beyond Newton because to take care of gravitational field energy. And if that was to be taken care, it should have been some term like this, not the del square A equal to 0. What really happens is, if you put B equal to 1, or that is to put, if the space part is flat, only the Newtonian potentials come into the metric, which is good enough to take care of your Newton's inverse square law. In that case, certainly the del square A will go as A prime square. Here is there some A prime over A sitting here. So this is this. So now from there, what is the lesson we did learn? The lesson we learn is that the gravitational field energy goes into making this B different from 1. It goes into the space part of the curvature. It doesn't need to be taken as a separate source on the right-hand side of the equation. And so which means that similarly, the vacuum energy, which is on the same status as the gravitational field energy, not being the primary source, the creation of the primary source matter should be taken care of by enlarging the framework. So here the gravitational field energy was taken care of by curving the space, and yet retaining the basic Laplace equation. So in a sense, the Einstein gravity could be roughly be considered, could be looked upon as the Newton in three space curve in this particular situation. And so similarly, the vacuum energy, which is a quantum creature, can only be taken care of in a similar fashion when I have a quantum theory of gravity, which will imply the enlargement of the space-time framework. And it is the question is of the enlargement of the framework, not rather than this thing. And so that's the another, in this context, another proposal has come by some authors, and where they say the gravitational field energy does not gravitate. And they modify the Einstein equation, and they write Einstein equation, the gravitational equation, in the trace-free form, and it is only the trace-free matter which gravitates, and the vacuum energy has trace non-zero, and hence it cannot gravitate. So first question is, it's against my general principle of universality. Everything which physically exists must gravitate, and we should realize, like the gravitational field energy also gravitate, but its contribution we take care in a more subtle way rather than in a direct way. This should be. Second thing about your vacuum energy, the analog of the second law is this. in the second law, moment we saw that m is 0, we asked for a new law. We asked for a new theory. Similar situation here. For the vacuum energy, rho plus p equal to 0, the way they're asking for. So from this itself, it means that this law cannot be taken up. We ought to ask for a new law, and which is to say the vacuum energy can only be taken care of by tapping some new property of space-time. What it is, that we still don't know because we don't have a quantum theory of gravity or quantum theory of space-time. Could it be higher dimension, non-commutativity, the fellow sitting here, or some new quantum relation? We really don't know, or something. So that's the question which we have to ask. Now the question about the higher dimension. The Einstein equation for gravity which I wrote, which first should ask is, in what dimension does it remain true? And the answer to that is, it remains true in all dimensions in which Riemann curvature could be defined. And the minimum number of dimensions required for the Riemann curvature's definition is 2. So in all dimensions greater than or equal to 2. Then we ask something. Gravity is a universal force, hence it must be present everywhere. It must propagate everywhere. If it has to propagate everywhere, it should have a free propagation. Then it turns out 2 and 3 dimensions are not good enough, or not big enough to let gravity propagate freely. And hence we come down to 4 dimensions. So up to this we came. So 4 dimensions are necessary for gravity. The question we are asking is, are the 4 dimensions sufficient? And for that I want to say that if I want to include the high energy effects of gravity, and whenever we are in an existing theory asking for a high energy effect, you would be asking for, so let's go to the higher powers of the basic variables you have. So we want to get to the curvatures, and then still you want that my equation should remain second order, and I should be able to define, it should be quasi-linear such that I should be able to define an initial value problem with a unique evolution. Then it turns out that the terms which the combination in which these things should have to be taken goes by the name of the quadratic terms Gauss-Bonnet, and in general the Lovelock. Now these terms make non-zero contribution in the equation only in dimensions greater than 4. And so question which we should say, like 2 and 3 dimensions were not big enough to accommodate free propagation of gravity. Similarly, 4 dimension is not big enough to include the high energy effects of gravity. So this is one motivation, again purely classical. The other motivation is that any classical field I have, the total charge in the universe must vanish. And this partly is, how do I create a charge? I start with something neutral, then something is taken out, one attains one polarity, what remains attains another polarity. This is how I create the electric charges. Now same should be true for the gravity. Now what is the charge for gravity? Is your matter energy momentum, which is unipolar. It's always positive or negative as you like it. Now the question is, if that is this thing, how does one balance this? The only other thing is the matter creates the gravitational field, and so to say the gravitational field must have an energy, and that should have a polarity opposite of opposite of the matter energy. And so the gravitational field energy should be negative, and this is the reason that gravity is always attractive. Or you can make a more general statement that the universal force will always be attractive because its interaction energy will be negative. But this situation is what? That I have a mass point here, the gravitational field is spread all over the space. So the field is non-localizable. Mass. So if I integrate over whole space, then this should be exactly balanced the positive mass. And here, a very simple exercise we could do about that you have a mass contained inside some radius r, could be the m at infinity when it's completely dispersed, and the gravitational field energy it has picked up when it has attained the radius r, that will go as m square over 2r. If I solve this quadratic equation, and that tells you that the mass goes to 0 as r goes to 0, or that is to say, as it collapses, the gravitational field entirely eats up the mass of the particle. And this is a simple back of the envelope calculation, tentative, but catches the base essential part of the situation excellently. Mode's rigorous thing is done in what goes by the name ADM, Ernovet-Dezher Misner calculation, which this happens. So now let us ask the question here, that if I take this, that I have mass point here, gravitational field is spread all over. Now consider a finite radius around this. Now in this radius, there is a total charge. The charge inside this radius is positive, is non-zero, because the gravitational field from outside this I have shielded out, and so this should be. So now, since this field is not balanced, the field must propagate of the free space. So it propagates of the free space, but as it propagates, its past light cone picks up more and more of the negative energy. And so the gravitational, so the propagation is not a free propagation, but it's a propagation with a diminishing field strength. It is something just very similar, but a dual to the situation what you have in the strong force case, where the gravitational field strength increases with r. Here the gravitational field strength decreases with r. And so the gravity can propagate in the extra dimension, but not deep enough. And so this is some picture which is very, very similar to the brain world scenario, which was popular some time back. But this is, again, tells you something similar. One more point I would like to say, that there is a kind of a duality it suggests between the strong force and the gravity, and maybe that ADS and CFT is another thing which enhances this kind of a view. Oh, I have only 5 minutes to do. Okay, then quickly I can go from this was the basic thing point, because this part is more technical, so let's not worry about. So what I said, the Riemann curvature, the Bianchi identity gives the gravitational, Einstein's equation for gravity. What happens if I take the higher orders in the Riemann curvature? And it turns out, does the same thing work? And the question is that, yes, it seems the same thing work. An analog of Riemann curvature could be defined like this, where this is a polynomial in Riemann with this sort of a thing which has a vanishing divergence. And I must say to my young people, everything which one writes here doesn't come out. I spent quite a while to get this part of thing. I was first bothering with this, and ultimately I write its Bianchi derivative and take its trace, damn thing doesn't vanish. Then somehow, I guess, why not put the damn thing inside? And that's where this thing comes. Then if you do this, so you have, now first thing we say, the Bianchi derivative cannot vanish. Bianchi derivative only vanishes of the Riemann tensor, because that defines the Riemann curvature as the commutator derivative of a vector. But to obtain the equation of motion, or on the left hand side, a divergence-free second-rank tensor, we don't need this. We need what to vanish is the trace of it to vanish. And that it does. And that exactly gives you the corresponding, the second-rank symmetric tensor. Then you have very interesting. So HAB is your analog of the Einstein. FAB is the analog of the Ricci. N equal to 1, this is the Einstein equal to the Ricci minus half Ricci. So it's a simple generalization, and this all works. What one can simply say is, corresponding to the each term in the Lovelock polynomial, one can write define an FABCD, and which gives you the corresponding second-rank symmetric tensor with vanishing divergence. And so this is one of the characterizations of the Einstein characterization of the Lovelock gravity. I can skip the other two, and let me come to lastly the discussion, because it's cruel to let people wait for lunch. Yeah. So here, so what we have done, we have explored some universal features of gravity and following some simple-minded common sense argument. The point which I want to say is, a couple of lessons which you can take with this is, it appears that the high energy effect seemed to ask for the inclusion of the higher order terms in Riemann in terms of the Gauss-Bonnet of the Lovelock, and which demand, they being non-trivial, higher dimensions. So this is saying the high energy effect of gravity seems to. Second thing, for the quantum gravity must always include the high energy effect of the classical gravity, and which would mean that this must also include this higher dimensionality. So what would you say? The classical gravity and general relativity relationship between them, truth should be the Lovelock gravity through the higher dimension. So this could be an intermediate stage. The vacuum energy, what we have to say is that the vacuum energy can only be incorporated in terms of in a way to the quantum gravity, it ought to be incorporated through enlarging the framework, not as a separate stress tensor. Other question which we finally should say, that we started with a very general property of space-time. It is its homogeneity which gave rise to ask for first a universally constant velocity, then it asked for a constant curvature which defined the radius of curvature for space-time, and it is for the observation to determine whether the radius of curvature is finite or 0. But more clearly, we should ask that the universal force or the gravity demands that space-time must be curved. The question then is, our own experience, what are the things which we see which curve? And it's only things which we see, the things which are material things which bend. And matter consists of bits, the quanta. So this also strongly suggests that if you want space-time to be curved, then deep down this should also have a quantum discrete structure. So the lambda in some sense could be intimately connected to the formation of space-time itself. Some indication in this direction is the Sorkin and his colleagues group who tried to construct space-time from the causal sets, and it seems to be that a constant curvature is a more natural construction than the zero curvature. Thank you.
Just a question from an astronomer. You mentioned at the beginning that you don't believe in dark energy, but you think lambda is there. But I think lambda, it could be one explanation for what we see. I mean,
lambda could be?
Lambda it could be a way of explaining what we call dark energy, right?
Yes.
So there is no contradiction in that with the data.
Oh, there is no contradiction. That's right. That's precisely the point. Yes, there is no contradiction. So what I'm saying you don't need those fanciful models for dark energy. Yeah.
So Naresh, I found your comments on lambda rather interesting. So what you're saying is that lambda is not really some extra source of energy or matter or whatever. It's just a property of space-time.
Right.
So just like C is allowing you to define the unit that
right.
relates X and T,
yeah.
there is also in addition an overall curvature, a length scale, which is a basic property of space-time.
Yes.
And of course, the mystery is why this length scale is so different from the
yes.
Planck length scale. That's maybe
that's
just another piece of physics, whatever. Yeah. Now, the thing is, when we go and look at the universe, assuming that people have got the cosmography right and it's beginning to look really good, what we see is that the curvature of the universe overall, I mean, we've got this matter and there's this lambda, and some of them conspire to give this very special flat universe. And yet each of them is non-zero. Whereas in your picture, these are really two different pieces of the physics. One is a fundamental property of space-time. The other is something to do with whatever the matter is doing.
That's right.
So is it then an accident? Sure. No, that's right. Yeah. But
lambda is giving space-time.
Very good. Uh-huh. No, you can. But why is it zero? Is that
omega lambda I have taken some value. With that, why it conspires that it is k equal to 0, exactly the situation. So that the question what I'm saying that I don't so much worry about k equal to 0. What I simply say, why should omega lambda has the value it has? Or which is the original value what Einstein needed to make the space is flat. Now to that the question is like so far, we haven't been able to explain the value of any physical constant. Why the value C it has, why the lambda it has. So I think it's the question which is beyond any theory what we have today. So it's a question which is open to, yeah.
Sir, you said the homogeneity of space and time dictated us that there should be a connecting constant which should have the dimension of velocities.
Yeah.
So particularly from this theory that we are developing, what dictates us that this velocity should have the magnitude of C. I mean, that was something from which Einstein started. But as we are incorporating this constant, is there something which dictates us about its magnitude?
No. So magnitude only comes from the electromagnetic theory, which you have, but there is no. This argument will never give you what is the value of C, because these are the general motivational arguments. You are not hungry?
You will be shocked. You had some picture of some Mars and then some various lines drawn there. Is it your attempt to imitate landscape painting of Monet?
No.